Hey guys, today we are working with the intermediate value theorem. If you have not yet had a chance to go look at the introductory ed puzzle, now would be the time to do so. Remember that while you watch the ed puzzle, you're just supposed to put any questions you might have here, new information you learn here, and reminders you may want to share with yourself for your future self to come back and look at these notes and know what the heck is going on can go here. What we're going to do in this section is we are going to work through some of these intermediate value theorem examples and talk about how to conclude or justify things using the intermediate value theorem. So first and foremost, it says prove that the function f of x equals this stuff intersects the x-axis on the interval 0 to 2, and then it wants to know, can the same be said for the function f of x equals this stuff? So for this first piece, what does it mean to intersect the x-axis? Well, it means that there would be some value that when you plug it into your function, you would get 0 out, right? If I intersect the x-axis, that means that when I plug something in my function, I get a y value of 0. So basically, we want to know that if my function crosses your x-axis. So the first thing that we look at if we want to try to use the intermediate value theorem is your function continuous on the closed interval? And since this function is a quadratic equation, quadratic equations are continuous everywhere in their domain, and quadratic functions, their domain is from negative infinity to infinity, so all real numbers. So automatically we can say yes, that this function f of x is continuous on 0 to 2. So that's how we're going to start off our justification. When we go to write our kind of skeleton for the intermediate value theorem, it's always since something happens. So we can say since f of x is continuous on 0 to 2, and for our and part, right, what the intermediate value theorem says that is if your function is continuous and one of your values, when I plug in one of my endpoints to my function, I get a number less than what I'm trying to find. And then if I plug the other endpoint in and I get a number greater than what I'm trying to find, or vice versa, right? As long as they're around 0, and that means that somewhere to get from my least value to my greatest value, I would have to hit 0 on this interval. So what we're going to do now is just make sure that that actually happens. So f of 0, if I actually plug 0 into this equation, I get 2. And then if I plug 2 into this equation, right, I'm plugging in my endpoints that I'm considering, excuse me. If I plug 2 into this equation, I get negative 4 minus 8, so that's negative 12, plus 2 is negative 10. All right, awesome. So now I can say since f of x is continuous on 0 to 2, and f of 2 is less than 0, whoops, that's not a good 0, is less than f of 0, right? My negative 10 is less than 0 is less than 2. I can say by the intermediate value theorem, by the IVT, there must exist some c on your interval 0 to 2 such that f of c gives me 0, aka your function f of x intersects, oops, the x-axis. Beautiful. All right, now let's consider, I obviously run out a little bit of room, so maybe find other place on your page, but can the same be said for this function f of x equals 2x minus 3 over x minus 1? And automatically, it should kind of kick off in your brain, no, we can't say this. And the reason for that is because of my rational expression, my x minus 1 in the denominator. What's the problem with this? The problem is that I know one place where this function would be discontinuous, right? If I plug 1 into this equation, I end up with an undefined answer because I get 0 in the denominator. So automatically, I can't use the IVT on this function because it doesn't satisfy this first piece that I need to satisfy. My function isn't continuous on the interval 0 to 2 because 1, the troublemaking part is in that interval. So no, the same cannot be said for this function. No. All right. Let's look at this next one. So in this next equation, so given the function f of x equals x cubed minus x squared plus 1, can it be said that there is at least one point c inside the interval 1 to 2, which verifies that f of c equals 0? All right, so right off the bat, we know our function will be continuous because this is a cubic equation, and cubic equations are continuous on their domain, and the domain of a cubic equation is all real numbers, so I know it'll be continuous from 1 to 2. So if you want to start off your skeleton, you're more than welcome to. So you can say since f of x is continuous on the interval 1 to 2. All right, and then now what needs to happen next is, right, I want f of c to equal 0. So what should happen if I can use my intermediate value theorem is that when I plug 1 in, I should get some value around 0. And then when I plug 2 in, I should get the other side of 0. So if we use 0, it would probably be one positive number, one negative number. Let's try it. So f of 1 equals, if I plug one of my endpoints in, if I plug 1 in, I get 1 minus 1 plus 1, which is 1. And then if I plug 2 in, I get 2 cubed is 8. 8 minus 4 would be 4, plus 1 is 5. Uh-oh. Neither of these don't surround 0. So like to get from 1 to 5, my graph doesn't necessarily have to go through 0. So actually, we can't use the intermediate value theorem here. So you can say the IVT does not apply because you can say f of 1 and f of 2 are both greater than 0. And so we can't use the intermediate value theorem. The intermediate value theorem says there's some intermediate value. This would be your intermediate value between two numbers, but 0 doesn't fall between 1 and 5, so we can't use the intermediate value theorem here. All right, in this next section, let's see what we got. The functions f and g are continuous for all real numbers. That's nice because when they give us that, we don't have to bother checking for IVT. The table above gives values of the functions at the selected values of x. The function h is given by this equation. Explain why there must be a value r for 1 to 3 such that h of r equals negative 5. Okay, so we already have that your functions are continuous, right? F and g are continuous, which makes h continuous. So since h of x is continuous, and then the interval we're considering is the interval they give us. So since h of x is continuous on the interval 1 to 3, and the goal is now that if I find two values, if I plug in my endpoints into my function, I should get values that surround negative 5. So I'm going to actually do that up here. So I'm going to do h of my first endpoint, h of 1, which would be f of g of 1 minus 6. Let's see, g of 1 is 2. So really this is f of 2 minus 6. And then f of 2 is 9, so I get 9 minus 6, which is 3. Okay, and then if I find my other endpoint, h of 3, then it would be f of g of 3 minus 6. Because I'm just plugging in those endpoints into my equation that I'm considering, and then I should end up with numbers that surround negative 5 to use the intermediate value theorem. G of 3 is 4, and then f of 4 is negative 1 minus 6, negative 7. Good, okay. And that's good because negative 7 and 3 surround my negative 5. So since h of x is continuous on 1 to 3, and let's see, h of 3 is less than negative 5 is less than h of 1, right? I'm doing my values here. My negative 7 is less than negative 5 is less than 3. And then we can say by the intermediate value theorem, by the IVT, there must be or exist a value, whoops, not W, a value R on the interval 1 to 3 such that h of r equals -5. Oftentimes, when you are concluding your intermediate value theorem, everything from here onwards, you can say by the IVT, basically what you're doing is you are just rewriting the conclusion they want you to come to. There must be a value r for the interval. So that's where I pulled that entire writing sample, was just from the question itself. You just had to show that you could use the intermediate value theorem, and then you can conclude what they actually want you to conclude. So there you go. All right, here would be an example of a multiple choice question with intermediate value theorem. This will be our last example we look at. So let f be a function that is continuous on the closed interval 2 to 4 with f of 2 equal 10 and f of 4 equal 20. Which of the following is guaranteed by the intermediate value theorem? Okay, so they gave us all the information. We know it's continuous, and we know that f of 2 equals 10 and that f of 4 equals 20. So there must be some value in here that equals some value in between 10 and 20. That's what the intermediate value theorem would tell us. And then that would be on the interval. This C value would have to exist in the interval 2 to 4 somewhere. Okay, so let's look and see which one of these things it says. So the limit equals, oh wait, let's start with the top. So f of x equals 13 has at least one solution in the open interval 2 to 4. So 13 fits in here. So that would be, I think that would be an okay statement to conclude, but I just want to go through and double check the rest of them as well. F of 3 equals 15. So it would be nice if f of 3 equals 15 because that would be a linear function, right? If this goes up by 1, this would go up by 5, but we don't know that for sure. The intermediate value theorem doesn't tell us exactly what function it is, just that there would be some value that exists between 2 and 4 that would produce an answer between 10 and 20. It doesn't tell us exactly what that value is. Same thing with this limit down here. We don't necessarily know that the limit equals that. And then you also have no idea, intermediate value theorem doesn't tell us anything about maximums and minimums, so you can get rid of those answers as well. So all we know is that we have one solution in the open interval, 2 to 4, is, or f of x equals 13 has one solution, because 13 fits in here, so that's that C value, there would be a solution that when I plug C in, I get out 13 automatically. Okay, so if you have any questions, feel free to let me know, but other than that, we are good to go.